Good evening, one and all. Is the audio clear? And video? Thank you. So, do you have any queries with regard to the previous session? We discussed about the concept of linear dependence, independence, basis, and dimension, and some of the problems. Any queries with regard to that? To anyone? Say. Or is that clear? All right. Then the objective of today's session will be, I just want to take some problems based on linear independence, dependence, subspace, basis and dimension concepts. Later, I move to the part that the concept of linear transformation and rank nullity theorem and problems related to that. So this is my whole idea with regard to today's session. So any queries? So please take a note of it. Then we begin our today's session. After noting, please tell. So let us take the problem that find dimension and basis for general solution W of homogeneous system Please take a note of these equations. So we are going to find the dimension and basis for the general solution W of homogeneous system. So here we need to understand that here you have three system of equations which is a homogeneous system. If you consider the solution space, the set of all possible values of x1, x2, x3, x4, x5, which is nothing but the solution space for this system, here it is taken as W. So for that solution space, you are finding the basis and dimension. In other words, if we have considered all possible values of x1, x2, x3, x4, x5, which are the solutions of this simultaneous system of equations, and for that 5D vector system, you are going to find the basis and the dimension. Okay? Any doubts? Is the question tag clear? Right. Now, as usual, it is just like finding or solving the homogeneous system. So just write the coefficient matrix here. 1, 2, minus 3, 2, minus 4, 2, 4, minus 5, 1, minus 6, and 5, 10, minus 13, 4, minus 16. So this is a homogeneous system having 5 variables and 3 equations are given. So reducing that into echelon form, we apply the operations as R2 tends to R2 minus 2R1, R3 tends to R3 minus 5R1. So it will be reduced to 1, 2, minus 3, 2, minus 4. And you will get the remaining values as, I think, so 1, minus 3, 2 will become 0 here. Again you will get 0. Again this will be 0. And you have the values 2, minus 6, 4. So again applying the operation R3 tends to R3 minus 2R2 will be equivalent to 2. 1, 2, minus 3, 2, minus 4, 0, 0, 1, minus 3, 2 is 0. So could you check on my values? Am I correct or not? So do you agree with these values? Please check. So all of you agree? Right. And then coming to that matrix, the rank of the matrix is 2, but we have 5 variables. So rank of the matrix is 2, number of variables are 5, it is less than. So the system will have infinite number of solutions. So how many independent solutions we will get? So 5 minus 2, this is equal to 3 independent solutions we will get. So generally we need to take 3 constants here. The interesting thing, if you observe, whenever a set of variables are given to you, depending upon the number of independent solutions, you will take the constants from the last. So usually we need to take x3, x4, x5 as constants. So if you take like that, from the second equation, from the row, these 3 will become constants. So it is not possible to find the values of x1 and x2. So because we have only one row left, if you take these 3 values as constants, the parameters, finding x1, x2 will be difficult. So for that, you take the constants as x2, x4, x5 as constants. We set like that. So you take them as constants, say a, b, c for our convenience, or you can take k1, k2, k3, whatever it may be. So if you take k1, k2, k3, the constants, then so from that equation you have x3 minus 3x4 plus 2x5 equal to 0. This implies x3 is equal to 3x4 minus 2x5. Since you have taken them as constants, so 3, say 3a minus 2b, where a comma b are constants. Or if you have given the address as x2, x4, x5 as this is constant a, this is constant b, this is constant c, you can take like this. So substituting the values in the first, you have x1 plus 2x2 minus 3x3 plus 2x4 minus 4x5 equal to 0. This implies x1 and 2a, because x2 you have taken as a constant, minus 3 into 3b minus 2c plus 2b minus 4c equal to 0. From this, x1 is equal to minus 2a, and could you give me the values of it? plus 7b minus 2c. Accepted? Yes or no? Right. So let us write the respective values here. I think this problem is given earlier in the previous year papers. So if you have written that x1, x2, x3, x4, x5, so x2 is a constant A, x3 is given as 3b minus 2c, b, c. So the three vectors minus 2, 1, 0, 0, 0, and then 7, 0, 3, 1, 0, and then minus 2, 0, minus 2, 0, 1. So these three vectors are nothing but bases. You can observe that they are linearly independent. You cannot write one vector as a combination of the others. Since you have three vectors are there, the dimension of the solution space is nothing but 3. Obviously, it is evident that as and when you find how many number of independent solutions are there or how many free variables are there, the number of free variables will indicate the dimension. The only thing we need to do is by taking the necessary parameters, the constants, you will find the basis for it. That is the only thing we do using the echelon form matrix. Okay. Yeah, I will say here. Let me say, let us write this thing first. Now see, from that equation, since there are three independent variables or three free variables or three independent solutions are there, we need to take three constants. Am I correct? Usually, we take the last three variables as constant, because whenever you take a homogeneous system, say I have taken a homogeneous system with variables a, b, c. The rank of the matrix is 2. Then I take usually the last variable as a constant, c as a constant, so that if you take a 3 by 3 system, the usual type will come as, here you have three values, here this value is 0, you will have two values 0, 0, 0. Since you are fixing that this variable is a constant, you are representing the second variable in terms of the third. So you can deduce two parts b and c. Substituting here we will get a usually. But here what happens, if you take the last three variables as constant, so this is a constant, this is a constant, this is a constant. Substituting the three values here, you need to find x1 and x2 still remain. So you need to find two values, but for which you have only one equation available, so which is not practically correct. So you are going to take the three variables in any manner. That's why we are taking x2, x4, x5 as constants. You will get x3. Not only that, you can take other thing also. You can take x1 as a constant. From that also, you can reduce x3, so you can get x2. So among x1, x2, I am taking one variable as constant. x4, x5 by default taken as constants from the last variables, and this will be reduced in terms of the remaining two. That's it. The whole idea behind it. Any doubts? So x4, x5, usually we take constants. Among x1, x2, you can pick up any one, either this or this, x1 and x2. So from this, x3 is dependent on these two, x4 and x5. That's it. Okay. right? Now, let me take some other problems. Is it enough for you in getting the answer, or you need any elaboration? Okay. Now let us take the problem that here I took a polynomial 3t square plus 5t minus 5. I want to represent that polynomial as a linear combination of the three polynomials p1, p2 and p3. So this is the problem based on linear combination. So since you know what is meant by linear combination, you just need to obtain the scalars by doing the simplification. Since the field is not mentioned here, by default let us take that A, B, C are scalars taken in the field such that 3t square plus 5t minus 5 is equal to A into P1 plus B into P2 plus C into P3. You need to find the values of the scalars ABC, hence you are done. So as we discussed earlier, the concept of vector spaces is applicable to every part of mathematics whenever you have similar structure is found. You can take the case of polynomials, functions, matrices, number system, anything you can take. The only thing is whether a set satisfies the criteria of vector spaces, then you are going to apply all these phenomena. Okay, so let us substitute the values here. So this is A into t square plus 2t plus 1 plus B into 2t square plus 5t plus 4 plus C into t square plus 3t plus 6. How to solve it? If you multiply all these things and if you take the terms taking common, because left side you have the highest power t square, t and constant is there. Similarly, by multiplying all these values, you take the respective terms as common. So if you observe that, it will be a plus 2b plus c of t square, 2a plus 5b plus 3c of t, and then you have a plus 4b plus 6c. This is the constant, simply by taking the terms as common. Now if you compare the respective coefficients, because we are assuming that the linear combination is possible here. If it is possible, what are the possible values of ABC? You are deducing actually here. So 3 is equal to a plus 2b plus c, 5 is equal to 2a plus 5b plus 3c, and minus 5 is equal to a plus 4b plus 6c. It is just like nothing but solving the system of non-homogeneous equations. So from that, as our friends mentioned here, a is equal to 5, and you are going to find the remaining values. Are you correct in getting the values? A is equal to 5, B is equal to minus 1, C is equal to 0, so that all the three equations are satisfied. If everyone agrees with that, then it is okay. So you can understand the importance of solving system of homogeneous equations and non-homogeneous equations under the concept of vector spaces. Actually, if you look into the syllabus, vector spaces are given first, then matrices are given. But actually the way of study or way of learning is matrices first, then vector spaces second. Because majority of the concepts of matrices we are going to use in solving vector space concepts. Okay. So if we agree with this solution, I will take the other part. So did you feel any difficulty in getting the solution of this problem? How to represent the linear combination? So please go through that. So you need to resolve the equation again. So I will say, by simply observing the pattern of equations, and you cannot apply the case of trial and error method here. Because from the first two equations, majority of the times you will get a solution by the trial and error case. But here you need to solve the system actually here. So you can take the augmented matrix, apply row operations, solve it. That is one method. Or simply solving the equations by eliminating the variables one after the other. That also you can do. You can apply any kind of method, but you should get the exact solution, not a solution by means of trial and error, which we won't accept. Because you are mentioning a specific linear combination here. So I can say you will get A as 3, B as 1, C as -2. You can check for that, I hope so. That will be the correct one. So by substituting these three values, these three equations are satisfied. Could you check? Yeah. So any doubts for anybody over this problem? Right. So let me take the other one. So please take a note of these vectors. I want to give some interesting concept for you. After noting, please tell. Now let us take that. I have considered the vector space R power 5, and in which I have taken a subspace W, and W contains these 5 vectors. And by default, assume that these 5 vectors are nothing but the spanning set of W. So if I have asked you a question that find a basis for W, what we usually do? We do that those 5 vectors are written as a matrix 1, 2, 1, 3, 2, 1, 3, 3, 5, 3, etc., etc. You are going to reduce that into row echelon form because you are applying only row operations here. From that, you will eliminate the dependent vectors, and here you will get a new set of vectors from the rows. So from the rows, after applying row operations, reducing into echelon form, you will get a new set of vectors which are nothing but a basis for the vector space. From that you will get the dimension. That is actually we do in the procedure. If at all the question asked that, apart from finding a new basis, I have given a set consisting 5 vectors, and my intention is among these 5, which vectors will form a basis for W. In other words, among these vectors, I want to eliminate the dependent vectors so that U1, U2, U3, U4, U5, among these, which U's will become a basis for W. That is my actual intention. For that, we will consider the matrix as vectors as columns in the matrix. So I will write the first column as 1, 2, 1, 3, 2. Second column 1, 3, 3, 5, 3. Third column 3, 8, 7, 13, 18. And then 1, 4, 6, 9, 7. Then 5, 13, 13, 25, 19. So it is nothing but taking the transpose of this matrix. So this technique is very useful for finding basis containing the original vectors. Without having new set of vectors forming a basis, we are getting a basis exactly with the original vectors taken. So how to do that? Here we apply row operations in the previous case. There we apply only column operations, and we reduce that into echelon form. So there is no difference in getting the echelon form here. We just do the column operations here. In other words, we can say it is column echelon form. So this should be 0. Here you should get 2 values 0. Here you should get 3 values 0. Here you should get 4 values 0, like that you are going. So in which, if you number them U1, U2, U3, U4, U5, on observing what are the dependent columns, you will remove them. The remaining columns are nothing but independent. So those vectors are nothing but the basis. So here we will form a basis by using the actual vectors in the problem. There you will get a basis with new vectors. That was the difference. Okay? Could you understand the logic here? Now let us apply the column operations there that you can do as usual. So C2 tends to C2 minus C1, C3 tends to C3 minus 3C1, C4 tends to C4 minus C1, C5 tends to C5 minus 5C1. That you are going to get. So first column remains as it is 1, 2, 1, 3, 2. So this will be 0. 1, 2, 2, again 1. Again you are performing C3 tends to C3 minus 3C1, 0, 2, again 4, 4, then you have 12, C4 minus C1, 0, 2, 5, 6, 5, again 5C1, 0, 3, 8, 10, 9. Again, by using this element, you are going to make the values as 0. Like that you are doing. Okay? So actually, there is another way of doing this also. Even though you have considered the vectors as columns of the matrix, since you are comfortable with doing the row operations, you just do the row operations without disturbing the pattern as it is. Don't perform the column operations, just perform the row operations as it is. Then, after applying row operations, I think say you are going to get resulting matrix as 1, 1, 3, 1, 5, 0, then 1, 2, 2, and then you have maybe some value 3, again 0, 0, 0, 1, 2, let me say, and the other values as 0. So this is comfortable compared to the previous one. So what is the only difference between previous method and this method? We consider the vectors as columns of the matrix as it is. We apply row operations as usual. We reduce that into echelon form, and then we observe the columns, what are the dependent columns and what are the independent columns. If you observe that this column is dependent on this is independent, you can make it 0. Again, you can say this column is independent and it is dependent on this. So what are the independent things that you can take? U1, U2 and U4. So these are nothing but the independent columns. First column is independent, you cannot make it reduced further. Second column is independent, you are going to reduce this. This column is independent and you are going to reduce this. So these columns will become 0 later. So U1, U2, U4 are nothing but the actual vectors which will form a basis for W. That was the idea. Okay. The procedure is very similar. We write vectors as columns of the matrix. We apply the regular row echelon form. Then we check which columns are dependent. We remove those columns. The remaining columns will constitute a basis for the given problem. That was the whole idea. Okay. Do you have any queries? How come independent? Let me say. So if you do the operations, these will become 0 and you will get some different values here. Accepted? Then again, using these columns, you are going to make them as 0 here. Agreed? So that's what I am saying actually. the selection is arbitrary. So whenever after applying the row operations, you will get an upper triangular matrix. The form of the matrix will be like this. In this upper triangular matrix, you are checking for the columns which are dependent on the previous ones. So those columns, on observing the column operations, you can eliminate them. Please understand, here I am not actually applying the column operations. I have applied only row operations. In order to get the independent vectors, I am doing the column operations as a rough work and understanding that these columns are dependent, so I want to remove them. So what are the remaining ones? In a general thing, you can observe that just there is no need to apply the column operations to here. Just observe, earlier you have the pattern like this. I think this is 3, right? Now see, these two columns have similar features. Two values are present, remaining are 0. Agreed? First two values are presented in the columns, remaining values are 0. Agreed? Whatever the numbers may be, accepted or not? So, among these two, you can fix one column. So, if I fix U3, then this will be dependent. The question is, can I make it 0 using this column C3 or not, the U3 vector? So, generally we give preference to the columns there 1 is presented. Usually we take 1 as the pivot element, generally the diagonal element. So since these two have identical features, we go with the first one. This is fixed, this thing will be taken as 0. Let me take another example that suppose you have the pattern coming like this. Now what happens? These three will have similar features. So this is fixed as independent. These two are dependent because they have the identical structure like this. So we exclude these two columns. This will be taken as independent one. Clear now? Similarly, while moving from left to right column wise, these two have identical features. 3 values are presented, remaining 2 are 0. So I fix the first one, the remaining columns will be eliminated. That's it. Okay. Yes, you can write U1, U3, U5 are also basis. That's what I am saying. You are fixing one and removing the others. The general thing is first come first. First one comes as first, which will be taken as basis. Because you are checking the structure based on the previous column. So we always stick on to the first one. First in first order, you can say for our technical conversation. First in first order. So while checking the pattern, this comes first. This has the same order, so remove this. Just like that. Okay? Fine. So this type of method, we call it as casting out algorithm or cast out algorithm. So what does it mean? Why? Suppose if you fix a column, you will check the pattern for which other columns have similar pattern. You remove them. So this one will be taken as independent. Like that we go. So as per the algorithm, you take U1, U2, U4 as the basis vectors. Okay, right? Now I just want to discuss some other problems. Can I? Fine. Just give me a moment, I will take the other ones. Now let us take the problem that I have taken three functions. So I have considered three functions f, g, h, where f of t is equal to sin t, g of t is equal to cos t, and h of t is equal to t, where all these functions are taken from R to R. F, G, H, all are defined from R to R. Now my question is, are they linearly independent or not? Now you can observe the difference between previous problems what we have solved on linear independence and this one. There you have given a vector, you have written a linear combination assuming that is equal to 0, and you have solved a system of equations. If you are able to find the values of ABC, the scalars, then it is dependent. If the values of ABC are only 0, it is linearly independent. That type of thing you have done earlier. But here it is somewhat different. You have taken the set of functions f, g, h, and you are going to verify whether these functions are linearly independent or not. Now, how to come up with this question if you are going to write the solution? Do you have any idea? Anybody? I think it is also given one of the previous year questions. Now let us write the linear combination first for our observation. So there 0 bar indicates the 0 function. Please understand, it is not a 0 vector because you are dealing with functions, the result is a 0 function. Now if you are able to find some non-zero values for ABC, then it is dependent. If you are able to prove that ABC values are only 0, 0, 0, then it is independent. Now how to get the ABC values here? Any idea? So is the question tag clear to everyone? What it is asked actually? Or you want me to repeat again the question part? Alright. Now see, the thing here is, since you are defining a function means every function will have domain and codomain, accepted? So you have written linear combination means for all values in the domain, you are observing that or you are considering that the linear combination is 0. So you are not taking the function for a specific value in the domain. For all values in the domain, you are stating that if linear combination is 0, can I get the values of ABC or not? That was the actual intention behind it. So since you have taken R and R, whole real numbers, in place of t, you can calculate f, g, h values for different values of t in the domain. So if you observe the pattern of functions, sin x, cos x and arithmetic functions are there. So what are the possible values usually take? So I can take t is equal to 0, t is equal to 90 degrees, pi by 2, t is equal to pi. So taking t values is at my will, because depending upon the functions I am taking t values, because the domain is taken as R, codomain is also R. The function is the function is sine cos t. Based on the function values, I can pick up any value in the domain. So, in order to get the values of ABC, we must have a system of equations. Because whenever a system of equations given to you, then only you are going to get the solution of it. So, for that purpose, I am substituting different values of t in this, so that I will get the respective simultaneous homogeneous system of equations. So, if you substitute t is equal to 0, then you have a into sine 0 plus b into cos 0 plus c into 0 is equal to 0 bar, which gives that b is equal to 0. Accepted? Then if you take t is equal to pi by 2, then a into sine pi by 2 plus b into cos pi by 2 plus c into pi by 2 equal to 0. You already got that b is equal to 0. So you have a plus c into pi by 2 is equal to 0. That is one thing you got with you. Again, if you substitute t is equal to pi, you have a into sine pi plus b into cos pi plus c into pi is equal to 0. Since b is 0, it reduces to 2. C into pi is equal to 0, which gives that c is equal to 0, because sine pi is 0. Since c is 0, automatically a becomes 0. So you have proved that all the values of a, b, c are 0. Hence, the given three functions are nothing but linearly independent. So in other words, you can say, maybe I am correct. If you draw the graphs of the three functions, they won't meet at single point. That means all the three functions will not meet at one point. That you can say. If they meet means they have a solution, right? That's it. That is my logic. So whenever functions are given, you write a linear combination as usual. In order to get a homogeneous system, you are substituting different values of t in that. The thing is, substituting these values is at your will. You can take 0, 45 degrees, 90 degrees, 180 degrees, anything you can take. I have taken these values so that equations will be solved very easily. You can take other things also. 30 degrees, 45 degrees, 60 degrees you take, you will get a homogeneous system, solve it. That is also acceptable. Okay. So substituting the values of t is user defined, that you can take. So please take a note of that. After noting, please tell. So can I continue? Okay. So the next thing is, I think it is also given in the previous year papers, I hope so. So here I have considered a vector space V whose dimension is 6. It means that if I have found a basis for V, it contains exactly 6 elements. And also I have considered two subspaces of V. So this is my V and these are two subspaces U and W. And I am saying that these are 4-dimensional subspaces of V and they are distinct. So U is a separate set, W is a separate set. There is no possible intersection of U and W. That means you can say that UV is not a subset of W and W is not a subset of U. Distinct in the sense you can feel like so. They are distinct. Now the question is, what is the possible dimension of UV intersection W? Any guesses to anyone? Now, let us write the formula which is known to us. Accepted? This formula we did already. Yes or no? Right. Now, you are going to find what is the dimension of UV intersection W here, what it will be. You know one thing that U and W have dimension 4. So this is 4 and this is 4. And this is not known, this is X. And how about this one? What we can say about dimension of U plus W? So for your convenience, I will give the idea that this is V, this is U plus W, and this is U. Here, U and W are distinct. So what happens if you consider the sum of the spaces U plus W, that is always bigger than U. If there is a possibility that U and W are same, then U plus W also has same dimension 4. If you understand that U is a subset of W, in that case U plus W is nothing but W. But he has mentioned that U and W both are different, distinct subspaces. So obviously this could be the hierarchy. So from this is 4, this is 6, and what you can say about U plus W? So this is the pattern that if you have written the hierarchy, U proper subset of U plus W and it is a subset of V. This is the exact hierarchy you will take. So if this is 4, this is 6, and what about this one? Can you say? What could be the dimension of U plus W? 5 or 6? Obviously it must be bigger than 4. The subspace dimension cannot exceed the vector space dimension. You have a possibility that U plus W may be equal to V, because he didn't mention that U plus W is a proper subset of V. He didn't mention that. So the possibility for U plus W is either 5 or 6. So if you have taken 5 here, dimension of W, U intersection W is somewhat different. If you take 6 here, dimension of U intersection W is somewhat different. So considering those possible cases, dimension of U intersection W is nothing but either 2 or 3. That was the solution. Okay. If you take 6, the value is 2. If you take 5, the value is 3. Okay. That was the answer. Is it clear to all? or do you have any other doubts? Right. Now, I just want to take one small definition here, and I want to conclude our today's session here since I got a small work outside. And tomorrow we will meet as usual. So, sorry for that inconvenience. I just want to give one definition here, then I will conclude our today's session. So just wait for a moment, I will fetch for a good example to you. Now consider the vector space R cube, the 3D space. Here I have taken two subspaces for it, possibly xy plane and say yz plane. Now let us do a small observation that suppose I have taken a vector three, 5, 7 in R cube. Now see one thing that I can write this 3, 5, 7 as accepted all. In the previous class, we have discussed that whenever two subspaces are given, W1 and W2, there we define their sum as W1 plus W2 is equal to every vector in this vector space will be of the form sum of two values, where one value belongs to the first set and other value belongs to the second set. This type of notation we call it as linear sum of subspaces. Can you recollect that? Say. So here R cube I have taken as the vector space. Here I considered two subspaces for R cube. One is xy plane, other one is yz plane. So here I have considered a vector R cube and I have represented this 3, 5, 7 as sum of two values, where first value belongs to u and second value belongs to w. Whenever this case is possible, we say that R cube is linear sum of u plus w. So not only x, y, yz plane, you can take other possible cases also. You can write R cube as a sum of other planes also. It is also possible. So what I am saying is, you are just partitioning the vector space. You are bifurcating the vector space into two parts, so that every vector in the vector space can be written as sum of two values. So here you can observe that 357 has two different representations. So you can represent 357 as sum of two values in two distinct ways. So in such cases, this type of representation we call it as only linear sum. However, if you have only one representation, whatever the vector you take, x, y, z, if it has only one representation, that sum of two values, in such cases we call it as direct sum. So for that notation, we indicate this plus with a circle around it. So we will write it as r cube is equal to u plus w. So what is the difference between linear sum and direct sum? Both have the same thing. Every vector in the vector space can be written as sum of two values. That is true for linear sum as well as direct sum. The only thing is, in direct sum, that type of representation is unique. In only one way you can write it as. Here, this representation is not unique. There are other possible ways to represent it as sum of two values. So direct sum is possible whenever intersection of the two sets is 0. So if you want a perfect definition for it, the definition of direct sum is given as, whenever you take a vector space, it is nothing but sum of two subsets, the subspaces, and their intersection is nothing but 0. Whenever this type of thing is there, we call it as direct sum. If only first thing is possible, second thing is not possible, in such cases we call it as linear sum. Okay? Any doubts over this definition to anyone? Or is it clear? Say. Right? So I want to conclude our today's session here. So tomorrow we will meet as usual. So that's all for today.